Hi, this is ET250, lecture 22, and today we're going to talk about power and AC systems. We're going to look at a plot of power. The instantaneous power we'll use as lowercase p of t, and see how it varies as your current and voltage vary in phase with respect to each other. We'll look at a simulation just to see what's going on a low level, minute by minute, moment by moment. And then we'll kind of dive into the more mathematical aspect. We'll look at this expression for the instantaneous power. And yeah, it might seem a little bit crazy, but I hope to break this kind of complicated expression down into three parts, 1, 2, and 3. And what I want to do is be able to extract out what these maybe more familiar terms, real power, apparent power, reactive power and apparent power are. And these three things come from this more complicated expression. We'll take all these three things, put them together, and maybe something you're familiar with, the power triangle, where you have S on the hypotenuse, P on the x-axis, Q on the y-axis. And then talk about a metric for how to quantify how good you are doing in terms of your using your available power. And that's the ratio of P over S, the real power over the apparent power. We'll do a simulation, and if you're still interested, you can see a proof of this. Okay, so let's begin. So let's look at this very simple system. We have some element, right? And this element could be connected to anything, and some current could run through it, and you could be measuring some voltage across it, right? Now, if you remember from our DC circuits or steady state circuits, if you want to calculate the power, you just have to multiply current times voltage. So this is the instantaneous power, and I wrote power absorbed because that's our perspective, right? If this is a positive number, this will be means this is absorbing power. If it's negative, means this is delivering power. Now, what about the equation? Well, the current is right now defined as going in the positive terminal, so therefore we use the positive version of this. If this current was defined as leaving, then we would use the negatives. Passive sign convention, no problem. Okay, so now in our AC world, we are assuming that I and V are sinusoidal waveforms, some amplitude, some frequency, the same frequency, and the same time, same cosine, but they might have different phases. Theta I and theta V might be shifted relative to each other. Okay. So what you'll see in the rest of this lecture is that P of t will oscillate at 2 times the electrical frequency of the current and voltage. Okay. We will introduce P, the real power, and that is actually the average of the instantaneous. This will oscillate, but P, this capital P, is the average, right? And now if P of t oscillates between positive and negative, just because it's oscillating does not mean it's going to oscillate all the way to a negative, from positive negative. It might stay all positive or all negative. But if it does go between positive and negative, there exists some power that bounces back and forth, and Q is the amplitude of that bouncing power. All right, so that's what Q is. All right, okay, let's look at a plot. I drew out a plot by hand. Okay, so let's look at a plot. And let's say that we're looking at an inductive system here. So an inductive system will look something like this, where we have a resistor and an inductor, let's say. Okay. Again, I still have I and V. I still have I going into the positive V terminal, but I and V are sinusoidal. And we remember from last lecture that if you have an inductive system, the I will lag V. Okay, if it's purely inductive, the I will lag V by 90 degrees. If it's purely resistive, however, the I will be in phase with V. And if R and L are present, then it's maybe somewhere in between. Okay, so let's look at what that might look like. And we have the voltage here in blue, and we have the current here in red. Notice the current in red is lagging the voltage in blue by an amount between 0 and 90 degrees. Okay. Now remember, the power is just the multiplication of I and V. So at any point, if I just take this point and this point, I get that point, right? This times this equals this. So I get a positive times a positive number, I get a positive number. Okay. Positive number times a positive number, I get a positive number. Now this is slightly less because these numbers are less. Okay. Okay, if I keep going down, oh, look at this. The blue voltage became 0. So it doesn't matter what the current is, the power is 0. Okay, good. Let's keep marching along. I have a positive and negative number. Well, it's going to be a negative. Okay. What else? Oh, I get another point where even though I have a non-zero voltage, I have a 0 current now. And so that brings it back to 0. Good. So the power is 0. Okay. And then we go here. Look at this. Negative and negative. We get positive. Okay. So the power kind of rectifies itself. 2 positives makes a positive. 2 negatives makes a positive. Okay. And then we come right back here. Now this time the current is negative, even though the voltage is positive, and we get negative power. Okay. And so I wrote out what I've been saying here is that the instantaneous power is 0 if either I or T are 0. And the instantaneous power is positive if I and V share the same sign. The instantaneous power is negative if I and V are opposite sign. And again, what does it mean if the instantaneous power is positive? Well, it means this thing is absorbing energy. What about if it's negative? That means there's a point where this is actually kicking back and delivering energy back into the system, the external system that it's connected to. And we also see, look at one period of velocity or current here. You can see that the instantaneous power oscillates 2 times for every 1 time. Okay. So and then the last thing I wanted to point out on this plot is that, look at this dashed line. That's right in the middle of this peak to peak. Okay. This line here represents the average, the time average of the instantaneous power, and we will call that capital P. We will call that capital P. Okay. And a little aside, we know that there's some negative here, and we know that there's some positives. So there must be some reactive power present. We cannot see exactly how much reactive power is present, but we know there's a non-zero amount. And we'll go into that later when we talk about the mathematical form of this. Okay. So let me pull out this other slide. And let's just review last lecture a little bit. So last lecture, we talked about Z and complex Ohms law. So what do we have? Some element Z, just like this. We have the V across and the I through. Okay. Now, if you recall from complex Ohms law, Z is V over I in this scenario. And if you remember our phasor introduction, if you divide phasors, you subtract the phase. So theta Z equals theta V minus theta I. Okay, good. All right, so let's look at the impedance for a resistor or inductor, sorry. So if you recall, theta Z L is 90 degrees, which equals theta V minus theta I. Why? Because the impedance is j omega L, which means it's a magnitude of omega L with a phase of 90 degrees. Well, what does that mean? That means theta V minus theta I, you're going to have an I lagging. Okay, so if we go to this plot and we go, well, what if we wanted the I to be lagging the voltage by 90 degrees? What's going to happen? This point, this whole red line is going to shift to the right more and more and more until this zero intersection aligns with this trough. Okay, can you imagine what's going to happen to the instantaneous power plot? As I shift this more and more to the right, can you imagine this instantaneous power plot is going to start dipping down and dropping? Okay, and so the instantaneous power would shift down and eventually it would oscillate about 0. This dashed line would lock in at the x-axis the second that this phase shifts by 90 degrees. Okay, and then the average would be 0. Now here's the thing: when you get to that point, energy is still existing, it's still flowing, power is still flowing, and energy is still bouncing. So there might be a misconception that the capital P is 0, the real power is 0, so there's no power transfer. Not at all. Not at all. There could be a lot of instantaneous power going back and forth, enough to kill you, in fact, right? And so in that situation, you would have a non-zero reactive power, even though the real power is 0. But you can see from here that the instantaneous power could still be very, very much non-zero, right? So and just to review, that's the case where this red line is shifted all the way 90 degrees and this guy jumps down. Okay, what if it was a pure resistor? So if it was a pure resistor, what's going to happen? If it's a pure resistor, the phase difference between the current and the voltage is 0. Okay, and then we can see that from our impedance, ZR equals R, right? Equals R with a phase of 0. So that means theta V minus theta I is 0. So that's like this current is shifting to the left now. And it becomes more and more in phase with the voltage. Okay, if that happens, can you imagine that the instantaneous power is going up, right? This little negative part is getting squished out. Okay, And so P of t shifts up. That means the instantaneous power while it's oscillating is always positive, right? It's always just touching. It's just touching the x-axis, but it's always positive, which means capital P is always positive, right? Now, even in this scenario right here that we've drawn, P is positive, average is positive, but there are times where this thing dips negative, okay? If it's a pure resistor, it never dips negative. It always just touches, right? Okay, now, if P, capital P is always 0, and if P of t, little p of t is always positive, well, what happens? Energy is only flowing one way. Okay, and that's kind of nice from the perspective of a power plant. You're just sending energy one way. You're not adding extra current and energy transfer to stress out your lines. Okay. Now let's look at the last scenario here. So we have, let's say, a capacitor. And so capacitor, the phase difference is it's not 90, it's not 0, it's negative 90. And that's theta V minus theta I, okay, from here. And we can go again, look at our impedance for a capacitor, 1 over j omega c equals omega c with a minus j on top. Remember, we bring this j up to the top, right, with a negative sign, which is the same as a magnitude of 1 over omega c with a phase of minus 90, okay? Similar, but slightly different. Well, what does this mean? That means like we've taken this current, we've slid it over, we're at a resistor situation, but then we kept going, right? We kept going. And so you can see that the instantaneous power plot would go up, but then right back down, right? It's like you overshot, you went too much, okay? And so P of t would still shift down, oscillate, just like the pure inductor situation. And eventually, if you got to theta zc equals negative 90, which is equivalent to theta v minus theta I as negative 90, which means I now leads the voltage by 90 degrees, P is going to be 0 because this average will fall onto the 0 line again, okay? And just like in this one, the energy would still bounce back and forth. Even though P, capital P is 0, it's tempting to say, oh, there's no power transfer. Well, there's no power transfer in the average. However, at any given instant, you could be bouncing power one way and back. This thing could be absorbing power and giving power, right? So don't get that twisted. All right, let's go look at a simulation and see this in action. So I'm going to go switch over here. And I'm going to go to this guy. All right, so what we have here is just our resistor and inductor situation. Notice I have the polarities labeled. I have an AC source, plus or minus Vs, plus or minus Vr, plus or minus VL, and I going from left to right. And notice the instantaneous power equation for those three elements are positive IR VR, positive IVL, but look at this one. I have a negative IVS because current is defined as leaving the positive terminal. All right, good. And let's run this for a second. What do we notice? Okay, so I'm going to put it on voltage and current so I can check out what's going on. Show voltage. You can see that the voltage is in green and when it's positive, and it's red when it's negative, and you can see it oscillating back and forth. The yellow denotes the current. Okay, good. And you can see it's going back and forth as predicted. And let's look at what's going on here in the resistor. That's easy. The voltage VR and the current I are in phase. Notice the green and yellow line. They're in phase, and look at the instantaneous power. As predicted, the instantaneous power is always positive. It's oscillating, but it's always positive, and it's oscillating at 2 times the frequency of the current or voltage, okay? The average of this instantaneous power is the real power, and you can see that it's also always positive. So what does that mean physically? This resistor at any given moment is absorbing energy. Yes, there are moments where it's absorbing 0 energy, just at those brief little points where the instantaneous power kisses the x-axis, but overall, you can think of it as absorbing energy at any given moment. Let's look at this pure inductor. This pure inductor, look at the current. The current is phase lagged by the voltage by 90 degrees. Okay, and you can see that the instantaneous power in white is oscillating now about the x-axis, which means the average P is 0, but at any given moment, you might have non-zero power transfer, whether it's positive or negative, okay? Okay, now let's go to the source. The source is kind of like measuring the power of the overall system here. And now because you have an inductor and a resistor in series, It's an inductive. So that means the voltage and current, the voltage source is not going to see a current that's perfectly lagging by 90 degrees. You can see it's lagging by somewhere in between, right? And so I'm going to stop it here. And you can see that the voltage here, here's the peak and here's the trough 0. And you can see the current in yellow is somewhere in between. So it's not quite at the peak and it's not quite at the trough. It's somewhere in between it, but it's lagging nonetheless. And now look at the voltage. The instantaneous power. The instantaneous power is kind of a combination of the resistor and the inductor. It's not oscillating all negative, right? And why are we on the negative side? Because of this negative. It's not all negative, but it's also not oscillating about 0, somewhere in between. And what this is saying is, just like the plot before, is that this in the average, this voltage source in the average is delivering power, right? Because negative means this guy is delivering power. But there are points in time right here that it is absorbing power. That means this inductor is kicking back energy back into this thing. It's bouncing it back, okay? And then let's just reason that out. Well, notice the 0 points are when either the voltage or the current are 0, good. And look at this. In this window of time, the instantaneous power is positive. Well, why is it positive? Voltage is positive, current is negative, so it's a negative number, times this negative here gets a positive number, good. Voltage is positive, current is positive, but I have a negative number, so I get negative. And over here, current is positive, voltage is negative, I have negative, but I have an extra negative, I have positive, right? And so you could just walk yourself through this little multiplication and you would see why the instantaneous power is bouncing and oscillating, right? Here it's oscillating, but not bouncing. Here it's oscillating and bouncing, okay, if that makes sense. So I just want to make a distinction between bouncing and oscillating. Bouncing means sometimes it's positive and sometimes it's negative. Oscillating means it's just going up and down, okay? The other cool thing about this simulation is that it can actually show power, and the green, instead of meaning voltage, means it's delivering power, and red means absorbing power. So let me run this now with that view. So look at the voltage source. When it's green, it's delivering power, and there's these little brief moments in time where it turns red. So green, 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 red. Green, 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 red, right? Look at the resistor. The resistor is always red. And look at the inductor. The inductor is kind of equal parts red and green, okay? So I hope this simulation kind of puts together how the instantaneous power looks like for these 3 different elements. Okay, let's go back to the document. Okay, so now let's take a little dive into the mathematical side of things now that we have, I hope, the intuition. Okay, so again, P of t equals I times V if we have I going into the positive terminal like so, okay? And let me have this plot just ready to go, just so we can refer to it. Okay, P of t equals IP cosine of omega t plus its phase times VP cosine of omega t plus its phase, good. And if we do some trig and algebra, we will get this expression that seems kind of crazy. And what I will go through it at the very end of the lecture. If you want to look at how it works, you can stick around, or you can just bounce early. This is the proof. I will go over this later. Don't worry about it now. What I would like you to do is just hit the make-believe button for right now and assume that this is true, okay? But we're going to slowly parse this out to make sure that you understand every single piece that's going on here, okay? So if you assume that this to this is true, we would be good for this lecture, and then we can prove this later. Okay, so what is this saying? Let's just follow this slowly. I have IRMS, VRMS. Okay, that's essentially IP and a scaled version of IP and VP. Why? IP, remember, IRMS is equal to I peak over root 2. VRMS is equal to V peak over root 2. Okay, so those are from here, good. Where's theta V, theta I? Good, good. So this is a constant, right? No dependency on time. Okay, so theta V minus theta I, good. And this thing is being multiplying this whole bracket. Okay, that's fine. So you have a constant out here. All right, and then what do we have? The number 1. Okay, that's not bad. And then what over here? Cosine of 2 omega t plus 2 theta V. Okay, we know what a cosine looks like. And that's just a phase shift. Not so bad. All right, and we'll even parse out what this looks like. Okay, what about this one? IRMS, VRMS, sine of theta V minus theta I. Okay, looks very much similar to this. Okay, constant, constant, constant. Great, no problem. Okay, let's look at, oh, sine of 2 omega t plus 2 theta V. Oh, we know what this is. It's just this, but just shifted by 90 degrees. All right, so none of this is that bad. They're just added together. So you essentially have the number one cosine times this added to a sine wave. Okay, yeah, it seems complicated, but it's really not that bad. Okay, so what can we glean mathematically from this description to help us describe some of the new things that we're looking at, and even some of this, right? Well, we can see that there's three terms. Good, 1, 2, 3. And notice I highlighted these in blue and this one in red, okay? And what else do we know? We note the frequency of the sinusoidal parts is 2 omega, and we already saw that here. This guy is oscillating at 2 times the frequency of the voltage and current because this omega is from the voltage and current. Good. Okay. What else do we see? Let's go to the next one. Okay. If we take the time average of this, we see that 2 and 3 are 0. If you take the time average of cosine, because it oscillates, it has equal parts positive, negative, that's 0. If you take the time average of sine, we have equal parts positive, negative. So this is 0. So the time average of this entire thing have 0, 0, and 1 times this. So the time average of P of t is IRMS, VRMS, cosine of theta V minus theta I. Well, what did we say the time average of the instantaneous power was? We said it was this line, good, which was capital P. Nice. So we now have an equation for capital P, the real power. It's IRMS VRMS cosine of theta V minus theta I. That is kind of nice. Why is that nice? Because I only need to know these 4 quantities, and I don't even have to do any of this craziness. I just need that part there, and I have the real power. I have the average of the instantaneous power. That's a useful quantity to know and pretty darn easy to calculate. Okay, and so this is the equation here. P, capital P, is the time average of instantaneous power, and it's equal to IRMS VRMS cosine of theta V minus theta I in watts. Great, okay. Now notice this is the real power. It does not oscillate because it's just an average, right? We don't want it to be oscillating if it's average. And it doesn't depend on T, good. And like I said, it's easy to compute if VRMS, IRMS, and the phase difference are known. Done. Okay. Let's look at 1 and 2. Let's look at 1 and 2. So I want to just plot, what does a cosine look like again? This, I mean, at this point, this should be mind-numbing review, right? Cosine omega t plus theta, if theta is 0. Oh, okay, easy, no problem, Chang-Siu. So we go between 1 and -1 for a cosine, good. If I shifted this positive, it shift to the left. I made this negative, it shift to the right, okay, good. What happens if I added 1, just like this? I have cosine and plus a 1. Well, it's gonna shift everything up by 1. So now the peaks go up to 2 and the average is now 1. No problem, okay? And it just touches the x-axis. Okay, easy. Theta equals 0 in this case, but if theta was positive, it shifts to the left, theta negative shift to the right. Okay. What if I multiply this whole thing by some value like capital P? Because this is essentially capital P now, right? Okay, what do we get? Okay, well, it looks like this. It's just a scaled version of this. Now the average is P, and look, it goes up to 2P, right? It still just touches the x-axis though and does not dip below. So look at this, terms 1 and 2 times this guy essentially look like that. Well, what does term 3 look like? It looks like a sine wave, right? It has some amplitude here in a sine wave. All right, good. Okay, so let's define P as this in blue, right? We've already defined this. This is the real power. But let's define a new term Q as IRMS VRMS sine of theta V minus theta I. Look at that. That's this guy here. So I'm going to rewrite this equation a little bit cleaner. Look how it starts getting not so bad, right? So I have P, which is this guy, good, times 1 plus cosine of 2 omega t plus 2 theta V, good. So that just means the phase shift is just 2 times whatever the voltage phase is, plus Q, that's this guy here, good, sine of 2 omega t plus 2 theta V, okay? And so this I have 1 and 2 in blue, and this guy I have it red 3. We know what 1 and 2 looks like. We actually know what 3 looks like. In fact, it looks like this, right? So 1 and 2 looks like a cosine where the average is P, and then it goes all the way up to 2P. And this term 3 looks like what? Just an oscillating sine wave at with an amplitude of Q. Okay, so if you were to add these two plots, you'd get this black one, if that makes sense, right? Because this black one here is instantaneous power, and that would be equivalent to the addition of this 1 and 2 plot plus the red 3 plot. Okay, good. So now what can we take away from this? Do we see some consistencies? Well, what did we say the average of the instantaneous power was? It's this capital P. Good. And now let's take the average of the red line. Well, what's the average of the red line? 0. What's the average of the blue line? P as well. Interesting. Interesting. So that should make sense. This P is the same dashed line here as it is here. That's nice. Okay. What else do we notice? We notice that terms 1 and 2 is, this is always positive, right? Okay, in this case, it's always positive, right? It's not bouncing back and forth, right? What else do we know? Look at 3. It is perfectly bouncing positive and negative. And look at this amplitude of this bouncing power is Q. And so I want to state this, and we want to be very clear, because sometimes it's hard to define what this reactive power is. You get a lot of questions. What's reactive power? Or what's imaginary power, right? Because sometimes they call this imaginary power. You'll see why later. And I want to state it clearly right here. Q is the amplitude of the component of P of T, which is number 3, that bounces back and forth. Q is the amplitude of the component of the instantaneous power, which is this one, that bounces back and forth. And we call this the reactive or imaginary power. Okay, so let's go back to this one. Capital P, the real power, is the average of the instantaneous power. It's the time average of the instantaneous power, aka the real power in watts. Q is the amplitude of the component of the instantaneous power that bounces back and forth. And we call it the reactive or imaginary power in volts, amps, reactive. Okay, let me say this one more time, just so that you really got this. P is the time average of the instantaneous power. P is the time average of the instantaneous power. Q, which you can't see on this plot, but you can see on this one when I dissect it out into these 3 components. Q is the amplitude of the component of the instantaneous power that bounces back and forth. Okay, that's what reactive power is. Is it really imaginary in the sense that it doesn't exist? No, it's imaginary only because of the mathematical term imaginary, because it will plot it on the imaginary axis. But it is not imaginary. It is definitely there, and it could definitely kill you, right? Okay, so Q is this guy, the amplitude of the component of the instantaneous power that bounces back and forth. You almost have to say that to yourself 3 or 4 times, right? Every week. Okay, let's keep going. So if we look at the definition of P and we look at the definition of Q, notice we have the same IRMS, VRMS, but we have a cosine and a sine. That's really nice because it looks like it's the X and Y axis of a right triangle. And some mathematicians and scientists realized this and went, well, instead of having to write out this, right, that seems cumbersome. Can we visualize it? And can we use our phasor math again? And the answer is yes. Look at this. They decided that you could write P on the x-axis and Q on the right axis, and you could have a P, Q, and S, a way to write complex power and S bar graphically as phasors. So all our phasor math is useful. Now, this angle here is theta V minus theta I. We are going to call that the power angle. In this plot, this power angle happens to be positive. It doesn't have to be positive, right? And then sometimes they just call this power angle can be negative, right? Now let's look at what's going on. We have this arrow, which is what we'll call the complex power, but all it is just a geometric way to combine P and Q, right? Makes sense. This S, if you can imagine, is just IRMS VRMS, right? Because that's kind of the length here. Because you can see that cosine is typically going to be less than 1, right? So this is a bigger number than P. Same with this one. This is a bigger number than Q, so it's the hypotenuse, right? And these are just everything broken down. P equals IRMS VRMS cosine of theta V minus theta I, good. Q equals IRMS VRMS sine of theta V minus theta I, good. S equals just IRMS VRMS, good. And what about this S bar? Well, if we write it in phasor form, we need 2 things, magnitude and direction. What's the magnitude? IRMS, VRMS. What's the phase? What's the direction? Theta V minus theta I. Why theta V minus theta I? Because of that guy there. Okay, so this is the complex power. This is what we call, the length of it is what we call the apparent power, and we use volt amps. So let's look at this. Watts, volt amps, reactive, volt amps. The reason why we use these different units for these three things, even though they all look like power, right? Volt times amp is power, is so that if you got a number like 7 volt amps, you would know, oh, we're talking about apparent power. If you got 3 VARs, you would know we're talking about reactive power or imaginary power. Okay. All right, good. So we have the power triangle. We have an idea of the instantaneous power. We have real power, which is the average of the instantaneous power. And we have the reactive power, which is what? The reactive power is the amplitude of the component of the instantaneous power that bounces back and forth. And this S is kind of like the total available power, the apparent power that could be chopped up between P and Q. Right? Can you guys imagine that? It's like what's available. Now, can you imagine if P and S are the same value? You're doing a good job. You're not having any power bounce back and forth. Whereas if your S is pointed straight up or straight down, you're not transferring any power in the average. Everything is bouncing. Okay, so that's the interpretation of the power triangle. Now, here's a little bit of mathematical notation that might help you in the future. So we're okay with this. The length and theta V minus theta I, good. We could say IRMS VRMS equals S, good. And this is in polar form, so we could write it in rectangular form. That's easy. Now, notice we have a minus sign. So sometimes you might see this, I asterisk V, and you might be like, what? I'm okay with this. I'm okay with that. I'm okay with that. I'm not okay with this one. What is this? Well, when you see the asterisk, all it means is it's called the complex conjugate, right? And it says make the phase or imaginary part negative to account for the negative theta I, right? So let's look at a little proof here. So if you want to just make this phase negative, I asterisk just becomes the magnitude of I with a negative theta I. Now remember, when you combine phasors and you multiply them, you multiply the magnitude and you add the phase. Look what happens. You multiply IRMS VRMS because it was the magnitude, and look at this. Theta V plus negative theta I becomes this. So this just accounts for the negative sign. It's just a compact way of writing this, so not too bad. Okay. Now let's say, remember we said we could use a peak or RMS version. Well, we would have to account for that root 2, and if you saw this form, you just have to divide by 2. No problem. Okay. This is just some. If you see this, you would know what's up. But hopefully, don't let it confuse you. Okay. So let's introduce our last term, which is the power factor. And the power factor is just the ratio of P over S. It's just this guy. So I'm going to rewrite this equation. Now, why do we want to have this metric, this power factor? Because instead of drawing the triangle and all this stuff, you can again reduce the number of things you got to talk about. You could just say, oh, I have a power factor of 1, right? And the power saying I have a power factor of 1 is a very loaded kind of thing to say. Well, what does it mean? It means I have AC power, instantaneous, bouncing back and forth, right? All that good stuff. And it's saying that the S on this power triangle is what? Is equal to P, right? Because power factor is the ratio of P over S, or just this cosine theta V minus theta I, right? So do you see that power factor is P over S? Yep, good. Or it's just this, good. What is it also saying if your power factor is 1? It's saying that my voltage and current are in phase. A lot of information there, right? Now, what you also have to say, if your power factor is not 1, you got to say if it's leading or lagging. Well, why do you got to say if it's leading or lagging? Well, the reason why you got to say it's leading or lagging is because this is a cosine, right? You can't tell. Let's say the power is pointing here or here, right? You can't tell if I give you a power factor number whether theta V minus theta I is leading or lagging. And so when you say leading or lagging, it's leading if I leads V, and it's lagging if I lags V. So leading, this is more capacitive, lagging is more inductive. And notice it's always current with respect to voltage. You just got to remember that. Okay, so if I say leading power factor, I leads V. If I say lagging power factor, I lags V. Okay, so let's do some examples of this. So let's say the power factor was 0.866, which is the equivalent to root 3 over 2. And if you do the A cosine, right, because, um, and, and so what if we want to get theta v minus theta I? If we want to do the A cosine of this, we would get plus or minus 30 because we don't know, right? The cosine is symmetrical. We don't know, all right? So you have kind of two options. You have the inductive version where you're pointing up, kind of like how we've drawn. And you have the negative version, which is capacitive, right? So here theta v minus theta I is positive 30 degrees, where we're lagging, and here's where it's leading. Can you see now why you have to, if you give a power factor number, you have to say leading or lagging? Because you just don't know. Now, like I said, if the power factor is 1 or unity, we have a pure resistor-like behavior, and I is in phase with voltage. Okay. So let's look at this last little plot of a cosine, right? And let's again put out our real power equation. P equals S cosine of theta v minus theta I. Power factor is cosine of theta v minus P over S, or equals P over S. This is our little element. We're talking about I and V. And if I plotted the cosine, it's going to look a little bit crazy, but let's say we have a cosine, right? And we have theta v minus theta I and power factor. Now we know that it goes positive and negative, right? I know this is kind of, but this is hopefully summarizing the story. Notice we can have 2 points, like let's say 30 degrees, where they're equal in value. But on this side, theta v minus theta I is positive, which means you are lagging, sorry. Theta v minus theta I is positive. Theta I is less than theta v, means you're lagging. So this is more inductive. And look at this. This is what the phasor plot might look like for the current voltage. The current is lagging the voltage, right? You could also have a leading power factor where, look, the current leads the voltage and we're over here, okay? Notice in both situations for this system, the power factor is positive, which means this system would be absorbing power. Because look, you'd have a positive number here and you'd have a positive number here. So you'd have real power being delivered into this system, right? So this is absorbing power. Now notice the power factor can be negative. And in this case, if this is negative, that means this overall capital P, the average of the instantaneous power, would be delivering power. This guy would be generating power, right? Okay. Now the current could still be lagging, right? But now theta v minus theta I is greater than 90. Can you see that? It's greater than 90, right? Okay. It's the same thing is true on the other side. If we go over here, you can be leading so much that the current is pointing the other way, right? And you're delivering power, but now you're leading. Okay, so this is the overall view. Leading on the left, lagging on the right, absorbing on the top, delivering on the bottom. And I got the 4 different phasor plots for these different situations, all for one simple little element. A lot of loaded stuff. You might have to rewatch this video a few times to really get it. Okay, do some homework problems, do some scenarios, but I hope this is a good summary of what's going on. I want to look at a simulation and then come back and look back at this one if you guys are still interested. But let's look at this other simulation I put together. Okay, so I'm going to share screen and go back to the simulation. So let's look at this next one. Okay, what do we got going on? Look at this. I have a voltage supply. I have a resistor. I have another resistor and an inductor. And what I want you to think about this system as, you got PG&E, our utility company, and you got the transmission line losses, or the resistance in the line. And let's imagine this entire system, these 2 branches on the right here is your factory, right? Maybe it's your power plant, whatever it is. Okay, so let's say your factory here, and your factory has a lot of motors. So we represent those motors with resistors and inductors, okay? And if we were just to operate this plant, let's just see what's going on, okay? And let's look at what's happening. We're operating this plant, and look at this. In the line, the transmission lines itself, look at this. You're burning power. This burning power is going to nothing. And look, you have 63 milliamps RMS of current here. Now, everything would be scaled, of course, so don't worry about the absolute number. But you have non-zero current in the transmission lines. Look at your overall power. Look how the current is lagging the voltage, and look at the instantaneous power. It's kind of bouncing back and forth. This is not good. Look at the instantaneous power of the resistor, always positive, good. And the instantaneous power of the inductor oscillates about 0, good. Okay, so this is all consistent with the last slide. And then look at the power. Look how the resistor is always red. The inductor is green and red equally. And here you can't quite tell, but there may be a little bit more green than red for the voltage supply. Now here's something cool. We have a capacitor here. And what we could do is we can power factor correct. Right now, the power factor would be garbage. Right now, the power factor would be nearly 0. Can you see why? And you go, why is it nearly 0? Remember, power factor is cosine of theta v minus theta I. And if I do here, if I have theta v is 0 and theta I is negative 90, if I do cosine of a plus or minus 90, what do I get? I get 0. Okay, so this power factor is garbage right now. And so PG&E would not like that. You would not like that because PG&E would charge you some more money. Well, what you can do here is you can click on this capacitor, and what we could see is hopefully these currents go down. So PG&E is happy because these currents go down, and you're going to see that the power factor goes to 1, which means the current and voltage now become in phase. What you're going to also see is that the current kind of bounces back and forth internally, and this capacitor helps to keep all the energy in here. What you'll also see is that this power, this dissipated power, which is actually useful power to you, is going to stay the same. So notice we have 40 milliwatts here. We want to maintain 40 milliwatts. Let's just double check that happens. I'm going to click this in. I got to let it reset it. I got to let it steady out. So I'll speed up the simulation. I'm going to run this. I'm going to speed up the simulation to get rid of all the transient. Remember, we got all the transient behavior. So that oscillates, yeah. And so let's bring it in back into steady state AC, right? Kind of weird thing to say, right? Steady state AC, but that should make sense. Okay, so here we're back into steady state AC. Let's look what happened. Look at the average of the instantaneous power now with the capacitor in place. It's the same, 40 milliwatts. That's good. So I didn't change the energy I was getting. Let's look over here. The instantaneous power of the inductor oscillates. And look at this. We have a little bit of capacitor voltage back and forth. And if you look at the current, let me slow down the current. Notice the current is now bouncing back and forth within itself. That's okay. But now the transmission lines have a lot less current. Look at this, 5 microwatts. That's nearly nothing at this point. And 300 microamps, that's good. And now look at the current and voltage in phase, right? And look at the power. The instantaneous power is all negative. It's oscillating, but all negative. That means this, look at this, look at the color. It's all green now. It's just green or 0, green or 0. That's nice. And so here's a situation of what we call power factor correction. We will talk about how to choose the right capacitors and how to tune all this. But I want to just show you an example of this now that we've talked about power factor, apparent power, reactive power. So here, no reactive power, all real power. Here, all reactive power, no real power. Here, all reactive power, no real power. Here, look at this, all real power, no reactive power. That's what we want, right? Okay. So I hope the simulation really kicked in and locked in what all this is about. Okay. All right. And again, these simulations, I'll be posting them in the description of this video. So please go and check those out. All right. So now let's go back and look at the proof of why that instantaneous power is what it is. If you want to check out at this point, go ahead. If you're still curious, I'll go back to the document cam and walk you through it. Okay, so stop share. All right, so let's look at this guy. So we have the instantaneous power, and we said is equal to the three terms, 1 plus cosine of 2 omega t plus 2 theta v plus q sine of 2 omega t plus 2 theta v. And so we're talking about this element. And P and Q, we already defined RMS, VRMS, cosine of theta V minus theta I, IRMS, VRMS, sine of theta V minus theta I, okay? All right, good. And so what can we do here? So I'm gonna just kind of put this, I like to have this plot next to us, right? Just to show us, is this the same thing? Yes, it is, good. Okay, so now what's going on here? Let's look at this. We're gonna start, so this is what we want. And we're going to start basically at first principles here. I'm going to start with I of t is IP cosine of omega t plus theta I, and VP cosine of omega t plus theta V. And notice I already wrote it in terms of an IRMS root 2, right? And we did that because we know that IP divided by root 2 is IRMS. Good. So we've already handled that. Now what we're going to do is take the instantaneous power and multiply them together. Bang, bang. And what do we get? We get IRMS VRMS times 2, right? Because I'm multiplying these all things together. And this times this. No problem. And we can pull out a trig identity. Cosine of A, cosine of B equals 1/2 cosine of A minus B plus cosine of A plus B. And notice I have that pattern. Look at this. A, B. No problem. Okay, this has a plus theta I. This has a plus theta V. So now I just pattern match. So look at this. These twos are going to cancel, and I'm left with this on the outside. Good. And look at this. On the inside, I have cosine of A minus B. That's the first one. So it's this one minus this one. Good. Plus cosine of A plus B. And it's just this one plus this one. Good. I'm just pattern matching the trig identity. Okay, fantastic. So what do I see inside here? Any cancellations? Yes, I do. Omega t minus omega t. Great. Theta I minus theta V. Good. And look at this. 2 omega t theta I plus theta V. Okay. And I have that written here. Okay, so what I want to do, if I want to get this to look like this guy with the theta V minus theta I, can I get theta V minus theta I in this equation somehow? Well, we know that cosine is symmetrical, so that means the positive argument and the negative argument are going to result in the same thing. We saw this already in the power factor. So this becomes theta V minus theta I on the inside, no problem. What about this one? What if I want a theta V minus theta I in here? That's a little trickier, but it's not too bad. Look at this, 2 omega t. And if I do this little trick, look, 2 theta V minus theta V, that's a positive theta V. And look at this, minus theta I. Look at that, that's a positive theta I. Little trick. But why is this trick nice? Because I got theta V minus theta I in both, right? Little mathematical trickery. Good. So this is the same as this. This is the same as this. Good. So I just rewrote that out. Theta V minus theta I. 2 omega t plus 2 theta V minus theta V minus theta I. Good. Okay, I'm getting there. I'm getting there. Okay, I can do one more trig identity. Look, I have another A and another B. And I look, cosine of A minus B equals the multiplication version. Cosine A, cosine B plus sine A, sine B. Oh, I think I can feel it. I can feel it. I'm close. So what do we have? IRMS VRMS cosine of theta V minus theta I plus, look at this first person. This is cosine B, cosine A, same thing. I just flipped the order. Theta V minus theta I, and look at this cosine 2 omega t plus 2 theta V. Oh my God, that's what's going on there. Good. And then look at this. Sine B, sine A, good. Theta V minus theta I, 2 omega t plus 2 theta V. Oh, that is it. That is it. That matches this. Because what do I have? IRMS, VRMS, cosine of theta V minus theta I, because that can be pulled out to the outside, times 1, because this would be a 1. And look at this, cosine of 2 omega t plus 2 theta V. Good. What about this one? I have IRMS, VRMS times sine of theta V minus theta I, because I can pull this one out, times sine of 2 omega t plus 2 theta V. This matches this and matches that. Yay. Okay, well, if you stuck around, thank you for sticking around. I hope that helped. And yeah, I look forward to seeing you in class.